me introduce now José Luis Viente from Tecnalia. So he's a senior researcher at Tecnalia, and he's going to present us advanced materials and a reactor for energy storage through ammonia core D. And the floor is yours, José Luis.
Thank you. I don't know if you can see my screen. No?
Yes, perfectly.
Okay, so because I so I want to thank you for inviting us to present the ARENHA project. The ARENHA project is it's a project, as you see in the title, is Advanced Materials and Reactors for Energy Storage through Ammonia. Some figures, sorry, yeah, okay. It's a research and innovation action that was granted under the topic Materials for Non-Battery Based Energy Storage. We started last year in April, and it stands for 4 years, and we have a budget around 5.7 million euros. And we are 11 partners, 5 of them are industries. Tecnalia is a coordinator, and we are working in membranes development, palladium base, or another membranes as well for hydrogen separation in ammonia decomposition membrane reactors, as well as recycling of the palladium membranes. The Eindhoven University is working mainly on the as ammonia decomposition membrane reactor design and testing at lab scale, as well in simulation. The National Center of Hydrogen in Spain is going to validate all the different prototypes we develop in real conditions. They have a testing plan with photovoltaics also on hydrogen, and also hydrogen fueling station, and all PEM system to generate electricity. Then we have the Denmark Technical University that is going to work mainly in sorbent materials for ammonia synthesis, as well for ammonia storage, and as well on direct ammonia electrochemical synthesis of nitrogen synthesis as well. And we have Fraunhofer and Elcogen working in solid oxide electrolyzer, Fraunhofer with electrolyte-based supported cells, and Elcogen with anode supported cells. And also Fraunhofer will also work in direct use of ammonia solid oxide fuel cells to generate electricity from ammonia reforming. And then we have our colleagues from United Kingdom developing catalysts for ammonia synthesis and catalysts for ammonia decomposition. And then Proton Ventures will develop the prototype for ammonia synthesis based on Haber-Loop's new design and with the sorbents. And Hydrogen Oxide will develop the prototype for the ammonia decomposition unit. And it was Peugeot, but now it's Stellantis that will work on using ammonia in internal combustion engines to improve and reduce the emission of the NOx or other compounds when using ammonia in internal combustion engines. And ENGIE is mainly dealing with the business case exploitation as exploitation manager, and also a life cycle analysis and economic assessment and process simulation as well. So why we decide to choose this the ammonia as the main hydrogen storage? Because we compare the different storage technologies, when seeing the storage capacity with the time you can have it stored, we see that in the chemical compounds, so power to chemicals is the easy way to have large amount of storage. And with this, we can solve the problems I have already raised before this morning already and before by my colleagues, that how to cope with the intermittency of the renewables and to increase the share of renewables in the energy production. So and to increase the renewables in electricity or power coming from renewables in different industrial sectors. So for this, we have to develop several technologies and to increase both the technological readiness level as well as the manufacturing readiness level. And we need to improve materials for different in the different application, and could be an electrolyzer or catalyst is able to work at lower temperature and pressure, because we have targets to reduce in the hoverboards, for instance, the pressure and temperature and so on. And so we have also to take into account the economic competitiveness of the technology we develop, and also the environmental aspect. And that's why we also have recycling, and we also work on using new catalysts with less platinum group metals, for instance. So why ammonia? Because it's between the carbon-free compounds is the one who has the highest energy density, volumetric energy density. It has a relatively low cost when you talk about large-scale production, but the idea in the project is to be able to increase the performance in all the prototypes to reduce the cost as well for the of the ammonia production and later on the use. Easy to liquefy because compared to the hydrogen, for instance, I think was minus 33 degrees, 1 atmosphere, you can have a liquid nitrogen, and maybe a 7 to 8 bars, you can have a room temperature, the liquefied hydrogen. Easy to store and transport. We have ammonia is already transport and stored since many years. So we have the knowledge is there, and finally it's carbon free. So the idea was to use ammonia as a green hydrogen carrier, and we have the activities we'll see later on that we cover all the power to ammonia two-stage value chains, and we will have some prototypes developed. So basically, we will deal with developing and integrating innovative solid oxide cell materials into a flexible high-temperature electrolysis demonstration unit at ambient pressure to be connected to a real photovoltaic plant. Also, we develop innovative material into a synthesis loop, enabling to operate flexible hoverboard production at lower pressure and temperature than the actual hoverboard process. We develop also in materials for ammonia decomposition and to generate pure hydrogen for different applications. You will see later on. And we also set the grounds to develop new materials and solutions for alternative direct synthesis and utilization of green ammonia. This will be done at a lab scale. And the idea is to demonstrate ammonia as a flexible energy carrier through the development of a fully integrated prototype for green ammonia synthesis and decomposition. And besides to this, we have also an activity regarding the social acceptance, techno-economic, environmental feasibility, and replication potential of the developed value chains. So as we go to the different work we will do, this is a summary of the power to ammonia two-stage value chains. We will work at the green hydrogen production with solid oxide electrolyzers, and also in the green nitrogen and ammonia production by electrochemical or electrosynthesis process. This now I show in the lab scale work. Also, we will work in advanced enhanced hoverboard loop, including sorbent materials for ammonia synthesis, and also to develop sorbent materials for solid state storage. And from this, we will have ammonia that can be dehydrogenated to produce hydrogen by a membrane reactor that providing hydrogen for generating power for electricity through a PEM fuel cell, or for a hydrogen fueling station. Or we have the direct use of ammonia through a solid oxide fuel cell for power generation, or the study and improvement of the use of ammonia in a combustion engine for mobility. And from this, we will develop the prototypes that I now highlighted in blue. That will be for the will be on a stack with the select one of the solid oxide electrolyte to develop next stack that will be included in the plant with the photovoltaic or renewable facilities. Then we will have the new prototype for the Haber-Bosch system also to be tested. We will use liquid ammonia storage as a storage for the prototype validation, and then we will have a prototype for the advanced ammonia decomposition that will be coupled to a PEM fuel cell and also to the facility for the fueling station they have in the National Center for Hydrogen in Spain. So if we look at the TRL status and what will be the TRL for the prototypes, we try to go to 5. But as I told you, there are activities that are going to be work at lab scale, and to set the grounds of, let's say, the future generation of green ammonia production. That I'm not going to go in details because you will have these slides. So let's go. So the idea is to increase the integration of renewable in the power system with large energy storage, to decrease the energy import dependency, because we will be able to produce the energy locally, or to import through ammonia. So that's also this the renewables is both onshore or offshore also. That's mainly for offshore that you can facilitate the integration. And we also keep the strategic European leadership in energy storage. So we also can have alternative energy import through renewable electricity storage and long distance transportation. So the cost of ammonia transportation is lower than the cost for direct hydrogen transportation, for instance. So in this way, we can decrease the amount of oil use or the CO2 emissions. As well, we study how the reduction of NOx emissions by studying the best way to use the ammonia in combustion engines, and this also could increase the future jobs as well, and the revenues. So some results from the project. I go to the main ones. We have defined the requirements and interface definition, so the battery limits between the different prototypes in the ARENHA value chains. We also have a modeled and also do some preliminary process flow diagrams of the SOEC system. The partners has been also working in decreasing the thickness of the electrolyte layers, or adding, improving the properties in the anode supporter cells as well. So changing the materials as well in the solid oxide electrolyzer. And they have been also working in the simulation model of the Haber-Bosch demo unit, as well as first looking for the best ammonia absorbent materials by doing genetic algorithm computational search on different materials. And also, we have studied the genetic barriers to assess the selectivity of nitrogen reduction versus hydrogen evolution in ammonia electrosynthesis. And we have also defined the operating condition of the ammonia decomposition, and we had also refined the experimental kinetic data membrane reactors models and definition of a new set of kinetic parameters for ammonia decomposition. That was in the modeling part of the work we do in the project. And regarding we have already developed some materials, so key components developments on the cells. Also, as I told you before, using thinner electrolytes or improved electrodes, or changing the layer and the modify active fuels and or air electrode layers by Alcogen. Also, they have been developing some catalysts. The idea is to work at lower temperature and than in the actual Haber-Bosch process, and with that using or using less critical raw materials. And also this for the electrochemical synthesis of ammonia. And we have developed the palladium-based membranes for hydrogen separation at Tecnalia. And we have also run some tests. You will show some results later on using ruthenium-based catalysts. That is a commercial catalyst that we will use for the prototype, but in parallel, we are developing, our colleagues from England are developing new catalysts able to work a lower temperature and without ruthenium, or let's put critical raw material like the ruthenium. You will see some results later on. And also we have Stellantis using with the help of the third party at the University of Orleans. They have an agreement. They have been working in demonstrating the potential of pure ammonia combustion in an internal combustion engine. They have identified is they need to put some hydrogen in the feed with ammonia, how the engine is working, and what is the no good components are released, how they decrease or no, depending on the working condition. Sorry, that is the next one. Okay, so here some few results. If you go to the Alcogen solid oxide electrolyzer, they have few developments have been done on using new materials and microstructural changes in their optimized state-of-the-art solid oxide electrolyzer. They have added some iron to the nickel network of the hydrogen electron active layer. They have doped with gadolinium and cerium elements as well, or they have changed the full active layer microstructure. So they are working on this, and depending on the best SOIC developed by Alcogen or Fraunhofer AKTS, we will select the best stack for the final prototype.
Jose Luis,
Yes.
I'm afraid we have to speed up a little bit. Can you finish your
yes
within 2 minutes?
Yeah.
I'm sorry for that.
2 minutes, I will finish. Yes.
Okay.
You see, here you can see is the blue dots as without no membranes. Here the line is the thermodynamic equilibrium. When you have you add the membranes, we have one bar in the permeate, you increase the conversion. When you have vacuum, you go over the limit of the conversion. The idea with the membranes is because if you remove the product, you are forcing the reactions toward the products. So that's why you increase the conversion. And here you can see the recovery. You can have a different temperatures. So, and merely you see the influence of the pressure as well. We got, was for 450 degrees. We nearly got 100% of conversion, and the purity, as you see, the range is very high as well. We have demonstrated that this reaction can stand 600 hour testing time. That was a lab scale. And also with the purity, we have still some ammonia above 50 to 20% of ppms, but adding a zeolite at the end, we have done some first trials. We have to work more on this. We can decrease. That was at 400 degrees. That's why we have around 80, 70 to 80 ppms. We can decrease to 0, but we are going to work to see, because I think the specification for the PEMs is 0.1 ppms. So that we have to measure on of ammonia. And okay, this is a summary of some main dissemination and communication. And that's all. If you have any questions.
Thank you very much, José Luis, for this nice presentation. And I'm sorry for having rushing
No,
you.
no, it's fine. It's fine. It's fine.
So there is actually one question. We take only this one. For the prototype you are planning, are you considering permanent integration between the SOEC and the Haber-Bosch process? Sorry.
I think these are not big scale process. This is one of the issues that can improve the energy efficiency of the project. The idea to have both is to have this integration, but I'm not sure that in the project we will be able to do this integration, because I think we will need more hydrogen and nitrogen for the prototype of the Haber-Bosch system, that the hydrogen that can be produced by the SOEC prototype. But this is something that for sure there will be done through modeling, for sure this. But I'm not quite sure that will be done at the level we have, because in the facilities, in the demo plan, we have also nitrogen, a large amount of hydrogen that is available, that could be made available. But the idea is to integrate both the SOEC and the Haber-Bosch process. This for sure, because I was just reviewing the project, and I see this one point to be studied as well.
Okay, thank you very much, José Luis.
Thank you to you.
Let's move to the next and last presentation before our working session. So let me introduce Sabina Furo, project manager at NV Park and coordinator of a Best for High project. Best for High project deal with recycling of end of